Hello and welcome back to another lesson on A-level physics. Today we are going to be looking at Newton's three laws of motion. The success criteria for today is to be able to recall Newton's three laws and to be able to identify third law pairs of forces. So let's look at the first law to begin with, and Newton's first law, or Newton 1, is that an object will either remain at rest or move with a constant velocity if the resultant force acting on it is zero. Now let's go straight into a task to do with that then. A car is moving around a roundabout at a constant speed. By considering Newton's first law, what can you conclude about the force acting on the car? Pause the video for 30 seconds, write down your answer, and then we'll talk about it. Okay, so the answer to that one is, because the car is moving around a roundabout, that means that it is accelerating, and so the resultant force must not be zero, and so the forces are not in equilibrium. That is what we can conclude from that situation. Okay, so if the resultant force on an object isn't zero, then the object will accelerate. That is Newton's second law. We are going to revisit this in more detail in a later lesson, but for today, all that you need to know is that Newton's second law can be given as an equation that the resultant force on an object is equal to its mass multiplied by its acceleration. It is important to consider that F is for resultant force. Newton's third law, in my opinion, is probably one of the worst answered questions that comes up on the exam. You will see in various textbooks, internet websites, etc., this idea of every action has an equal and opposite reaction, and students will quite commonly quote that when asked what Newton's third law is, but that is a very, very lazy definition to be given for Newton's third law. What you should be saying instead is that if object A exerts a force on object B, then object B will exert a force of equal magnitude on object A in the opposite direction. This is a much more specific way of stating Newton's third law, and this is how you would apply it to any context in which Newton's laws of motion apply. Now, we have something called Newton's third law pairs, and to be a Newton's third law pair, the forces involved must be of the same type and they must act on different objects. We're now going to look at two situations where Newton's third law applies, and we're going to be using the phrasing from Newton's third law to explain what is going on in those situations. So the first situation is this man leaning on a wall. So you've got the man leaning on the wall. Now, if the man is leaning on the wall, he puts a force onto the wall, and of course the wall is putting a force of equal magnitude back onto him, but in the opposite direction. So if you were asked to state how Newton's third law applies here, you would say the man puts a force onto the wall, and the wall puts an equal force onto the man in the opposite direction. And that is how you would apply Newton's third law to that situation. It's exactly the way it looked on the previous slide, but you're replacing object A with the man and object B with the wall. And now here we've got a jet engine. One of the most common questions that get asked by engineering students is basically, how does an exhaust work? Why does that cause a force? Well, here we've got a jet engine that has got lots of gas inside of it at high pressure. Now, you know that the gases are ejected from the jet engine and that makes the engine move forwards. So here, essentially what would happen is that the gas would put a force onto the engine, and so the engine puts a force of equal magnitude onto the gas, but in the opposite direction, and thus the gas is expelled, and that's what causes the movement to take place. So let's look at two example questions then. The first example says a man of mass 60 kilograms is sitting in his chair and he is stationary. The first thing that we've been asked to do is calculate the weight of the man. So to do this, very straightforward calculation, we know that weight is equal to mass times gravitational field strength, and so we do 60 multiplied by 9.81, which gives us an answer of 589 newtons, no problems. For part B, it says draw a diagram to show the direction of the two forces acting on the man. So obviously the weight is going to be one of the forces that acts downwards, but there is going to be a force balancing him going upwards because he is in contact with the chair, and so we have that normal contact force or support force acting upwards. You can call it normal contact, support or reaction force. It doesn't make any difference. Now then, the end of that question says that do those two forces make a Newton's third law per? In actual fact, they don't, because to be a Newton's third law per, the two forces have to be the same type of force, and here they're not. One of them is a weight force caused by gravity, and one of them is a support force, and so they are different types of forces. Additionally, the two forces would have to act on different objects to be a part of Newton's third law, and both of these forces are acting on the man, so that is a second reason as to why this is not a Newton's third law per. Okay, second example says a ball is dropped from the top of a building, and we need to draw a diagram to show the forces that act on the ball as it falls. Well, the force that's going to pull it down is going to be the weight, but obviously as the ball falls and it picks up speed, the drag force or the air resistance is going to increase, and so the air resistance acts upwards. Now, it doesn't say in this question whether we've reached terminal velocity or not, so it doesn't matter how long you draw that air resistance arrow. Obviously, if we were in a point where the ball was accelerating, then the weight would have to be bigger than the air resistance, and if we were at a point where we had reached terminal velocity, then the weight and the air resistance would have to be drawn to the same length. Now, part B says, how can Newton's third law be applied to this situation? Well, it's not to do with the weight and the air resistance. It's to do with what is causing the weight on the ball. The Earth, because it is so large and has its own gravitational field, is exerting a force onto the ball. So the Earth exerts a downwards force on the ball, so the ball exerts an upwards force on the Earth. So believe it or not, as that very small ball is falling towards the Earth, it is pulling the Earth towards it. But because the Earth is so large, obviously the motion of the Earth isn't noticed, but the motion of the ball is what we observe, because the ball is so much more small than the Earth is. Okay, let's go into some summary questions then. There are three levels of summary questions. We've got consolidation questions on pink, we've got standard demand questions on yellow, and we've got stretch and challenge for students going for the top grade in green. So the first question on consolidation is: a car of mass 800 kilograms accelerates uniformly along a straight road from rest to a speed of 12 meters per second in 50 seconds, and we were asked to calculate the acceleration of the car. So to work out the acceleration of the car, we know that acceleration is change in velocity divided by time. The velocity has changed by 12 meters per second in a time of 50 seconds, so the acceleration will be 0.24 meters per second squared. Obviously, please make sure to include the unit when you're writing this out at home. Part B says calculate the force on the car that produced this acceleration. Now, Newton's second law can be written as force equals mass times acceleration. So we'll do the mass, which is 800, multiplied by the acceleration that we've just worked out to be 0.24, which gives a resultant force on the car of 192 newtons. And then part C says calculate the ratio of the accelerating force to the weight of the car. So by that, it essentially wants us to work out the weight of the car, and a ratio, we'll do one of them divided by the other one to give a ratio. So the weight, we do mass times gravitational field strength, which gives a weight of 7,848 newtons. And then to work out the ratio of the force to the weight of the car, we divide the force by the weight to give an answer of 0.024. Question 2. An aeroplane of mass 5,000 kilograms lands on a runway at a speed of 60 meters per second and stops 25 seconds later. Calculate the deceleration of the aeroplane. Probably the easiest way to do this is to use acceleration as change in velocity over time. Again, you could do it using SUVAT as well. Now, the change in velocity is it's gone down by 60 meters per second in a time of 25 seconds. So that would give us a deceleration of 2.4 meters per second squared. Then to work out the braking force, again, it's a case of using F equals ma. So we do 5,000 multiplied by 2.4, which gives us 12,000 newtons. You can include a negative sign if you want to indicate the direction of the force, but you don't need to get the marks for the question. Standard demand begins by asking us to identify each of Newton's laws in action. So we've got a stationary ice skater pushes his partner away and finds himself moving in the opposite direction. Which of Newton's laws predicts this outcome? Well, that would be Newton's third law, because if the ice skater has put a force on his partner, then his partner puts an equal force on the first ice skater in the opposite direction, which means he will move away, of course, in the opposite direction. So the answer to 1A is Newton's third law. The law which can be used to predict the acceleration of each skater after the push is going to be Newton's second law, using the equation F equals m times a. And then part C, after he's pushed his partner away, the skater glides at a nearly constant speed across the ice without any effort, as the frictional force acting on him from the ice is negligible. Which of Newton's laws predicts this would happen? So if you remember, Newton's first law was that the velocity will not change as long as there are no resultant forces acting. Well, if there's no resultant force, he'll move at a constant speed, and so that would be Newton's first law that tells us this. Question 2. A bullet of mass 0.002 kilograms travels at 120 metres per second into a tree, and it penetrates 55 millimetres into the tree, and we want to calculate the deceleration of the bullet to begin with. The easiest way to do this is, of course, by doing SUVAT. So we can lay out what we know. We know that the bullet moves 55 millimetres into the tree. So the value of S is going to be 0.055 metres, of course converting millimetres to metres. The initial speed of the bullet is 120 metres per second, and because it is brought to rest, we know that its final velocity is going to be 0. Now we need to choose an equation that will help us find the value of A. So we need an equation that links S, U, V and A, and the equation that links that is V squared equals U squared plus 2AS. We now need to rearrange this equation, of course, to help us get a value of A, a value of S. No, it is a value of A that we want. My apologies, there's a typing error on the screen, but never mind. So it will be A equals minus 120 squared over 2 times 0.055, which should give you an answer of minus 1.3 times 10 to the minus 5 metres per second squared. Of course, I'll just point that error out to you in case you are using this without the sound on. That there should be A and not S for the arrangement. Lovely. Okay, carrying on then. Carrying on. Part B wanted us to work the impact force on the bullet, so we'll be using F equals m times A. The mass, of course, is 0.002 kilograms. We've just worked out what the deceleration was, so we multiply those together and the product gives us 206 newtons as being the force on the bullet that causes it to decelerate. Now finally we come on to the stretch and challenge questions. These questions are actually about a practical that you haven't done, but on paper 3 of the A-level they will be giving you practical investigations that you haven't done and you have to apply your knowledge to them. So let's read through the information and see what we are asked. It says a group of students investigated the acceleration of a trolley. The acceleration is caused by a falling mass. The time taken for the trolley to travel a distance of 1 metre from rest was measured 3 times for different values of falling masses. Below is a list of common errors that some of the students made in this investigation. We need to identify whether each of these errors is a random error or a systematic error and comment on the effect that each of these errors may have on the results. So the first error that we're going to consider is that the student didn't observe the trolley at eye level at either end. Instead, she stood in the middle and took measurements rather than moving along the side of the ramp as the trolley moved and observing the trolley at right angles. So essentially what she's done there isn't what's shown on the diagram. If I go point out here, she hasn't observed it from there, and there she has just stood in the middle here and made the measurements from there. Now that obviously is what we call a parallax error, so you will get a mark if you refer to the fact that this is a parallax error. Now that means that she won't time a complete distance of 1 metre because the trolley will be seen at the starting position when it's actually past the starting position, and it will be seen to be at the finishing position before it's actually reached it because of this parallax error. Now the error will be the same each time, so regardless of how much mass she has on the mass hanger, the error is going to be the same each time, and so this is a systematic error. So it will be 1 mark for referring to the fact it is a parallax error, and a 2nd mark for referring to the fact it is a systematic error. Part B, the student did not include the mass of the mass hanger when adding up the masses used to accelerate the trolley. Now, that just means that because they've not included the mass of the mass hanger, the force that's acting on the trolley will actually be bigger than what the student believes it's going to be. But that wouldn't be too much of a problem because obviously it will be by the same amount each time. Because it is by the same amount each time, we say again that this would also be a systematic error. Now part C is that the ramp is not actually horizontal, but it's sloped down slightly at the end where the mass hanger was. So rather than this being perfectly parallel the track, it's obviously tilted slightly. Now that means that a small component of the weight of the trolley is actually going to act down the slope and cause it to accelerate. So the force that is acting on it will be larger than what the student believes, but again, because that slope isn't going to change, this is going to be another systematic error. Then finally part D, the student measured from the back of the trolley as the starting position and stopped the stopwatch as soon as the front of the trolley passed the finishing point. Now if you think about what the student was trying to do, they were timing the distance it takes it to travel a metre. Now if they start the timer from the back of the trolley and then look when the front of it reaches the finishing point, it hasn't actually travelled a metre when that happens. But again, that is going to be a systematic error because the distance that is wrong will be the same by the same amount each time. So it is, of course, a systematic error.